Welcome back to our course on blockchain and its applications. So, in the last class we have seen that how fork impact the consensus finality in a proof of work consensus mechanism, and we have discussed different kind of attacks which are possible on proof of work, and as well as we have discussed about the possible monopoly problem and the 51% attack that can happen on proof of work. So, today we are going to look into some other limitations of proof of work, and at the same time we are going to discuss about the consensus mechanism in a open network or in a permissionless network which have been developed to mitigate those problems of proof of work. Now, the broad topic that we are going to cover today is the different consensus mechanism which are been designed based on the limitations of the proof of work mechanism. So, basically we are going to cover three different consensus architecture, which is called the proof of stake or POS, proof of burn POB, and proof of elapsed time or POET. So, to start with, let us try to look into the limit of proof of work. So, the good thing in proof of work is that it provides a fully decentralized consensus mechanism for permissionless model. So, that means in an open environment you can reach consensus which guarantees at the minimum level of safety and the liveness property of the consensus, although immediately it is not been able to guarantee the consensus finality, but eventually that is guaranteed by putting up certain constraints on the use of the transactions that are getting committed with the help of these blockchain operations. Now, this kind of architecture, what we have seen that it works good for cryptocurrencies, at least it serves the purpose that was been originally envisioned for the design of cryptocurrencies. It has been able to provide a free and open marketplace where people can trade with a currency that is under that is under a kind of entirely open environment. So, no bank or no government would be able to control the flow of the money. So, it is entirely depending on the underlying algorithm based on which the money is getting flowed and the transactions that people are generating. So, that way in a cryptocurrency domain, the objectives that have been envisioned by the developer of cryptocurrencies that are being satisfied. So, that is the kind of good thing behind this proof of work consensus mechanism. But the bad thing in proof of work consensus mechanism that here, although you are not trusting any individual, so that is the kind of our hypothesis. So, that is why we say that this kind of blockchain architecture based on proof of work consensus, it can provide a trustless environment. You do not need to explicitly trust individuals to reach to a consensus, but inherently here you need to trust the society as a whole. So, what you need to assume? You need to assume that your network is so large that an attacker will not be able to gain more than 50% of the hash power of your network. Well, so your network is sufficiently large to prevent the 51% attack. Well, but this is a kind of strong assumption particularly for many enterprise applications where blockchain is likely to be suitable. Well, so in applications like Bitcoin, where it already has an established network and there are millions or billions of users in the Bitcoin network who have participated there, obviously it is much more difficult to raise the 51% attack there. But as I have mentioned that it is not like that no one have ever demonstrated 51% attack, although it was not possible on Bitcoin, because by the time people have understood that 51% attack is possible on proof of work blockchain, the Bitcoin network has grown sufficiently large, well, to prevent the 51% attack. But that is actually not true for the future open blockchain architecture, because the attacker already know that such kind of 51% attacker they can launch, the 51% attack that they can launch, and that way whenever you are proposing a new blockchain architecture or rather a new blockchain application with proof of work consensus mechanism unless you are being able to ensure that during the bootstrap itself your network will be sufficiently large. Well, so if you are not being able to ensure that, then for an attacker it is much more easier to raise the particular attack on those systems. So, for example, if you just take enterprise applications like the supply chain management that we talked earlier as well. Now, in a supply chain management you have limited number of stakeholders, you have certain vendors, certain refineries. If I just think about a petroleum supply chain, the example that we have talked about earlier. So, you have certain refineries, certain distributors, then certain retailers and so on, and your network is not that large. Well, now if I can compromise few of the peers in your network, in your blockchain network, then I can possibly compromise the entire network. Well, so that way during the bootstrapping itself you need to ensure that your network is sufficiently large, which is really very difficult for a new application. So, for a new application you cannot say that, well, tomorrow I would be able to ensure that this application has more than millions user or more than even 5,000 users who are simultaneously using the application. So, for an attacker to compromise the application, at least the attacker need to take control of at least 2,500 different users. So that is something very difficult to ensure. Well, now because of that reason, that poses a limitations for, as I mentioned earlier, that for Bitcoin it was good, because by the time the attacker has understood that 51% attack is possible, the Bitcoin network has grown up sufficiently larger. But that is not true for the future proof of work blockchain network. So, the question comes here that how we are going to ensure that 51% attack is not possible on my network. But the really problematic thing with proof of work mechanism is that it has severely low transaction throughput. Well, and at the same time it overuses the computing power. So, if you just look into Bitcoin, so Bitcoin supports around 3.3 to 7 transactions per second, whereas Ethereum support around 15 transactions per second. Considering a global scale, a complete open network, this is actually something very low. So, if you just think about your standard monetary systems like Visa or MasterCard, they possibly support more than 5,000 or 10,000 transactions per second. Well, so that way the transaction throughput for Bitcoin is really very less. Another problem that I have mentioned is the overuse of power, well, or overuse of computing power. So, if you just look into the Bitcoin network, there are millions of miners. Well, so you can just assume, well, at least or at most 1,000 or 5,000 of them are active simultaneously. But even if that is the case, only one of the miners will be able to propose the next block, or even if you are thinking it as in the form of a mining pool. So, maybe a few miners in the mining pool can collectively propose a new block. Well, but the thing is that the person who has been able to propose the new block, the block which is getting added as a part of even the main chain, only those miners are getting the reward. Well, others are not getting anything. Even if you are been able to successfully mine a block and your block is getting added as a fork, then also you are not getting any reward. Well, so if you look into a standard Bitcoin block, so the first transaction of the block that we call as the Coinbase transaction. So, this Coinbase transaction actually indicates the mining reward. Well, now the moment a block becomes forked, so this Coinbase transaction for that particular block becomes invalid. Well, so that way only one person or only one mining pool get the reward, but thousands have tried to do that. So, thousands have investigated thousands have invested their computing power. Well, so those computing powers are actually in a total loss. Now, if you just look into the energy consumption that is taken up by the Bitcoin transactions, if you just try to plot it, this is the kind of curve that we have over time, and you will see that the amount of terawatt hour. So, the left hand side, so that y axis, that unit is in this y axis has an unit in terawatt hour. Now, you can see that over the time this amount of energy consumption increases significantly. Well, and the estimated terawatt hour per year was around 157.74 terawatt hour in August 30, 2021, a kind of very recent stat. Well, so if you just try to look into that, so that is a kind of huge amount of energy that is being devoted to mine the to mine a new block in a blockchain. So if you just try to compare it with other energy consumption sources, so what you can see that so the carbon footprint that is being generated by this Bitcoin transactions, it is around 825.47 kg per transaction. So that is actually huge. Well, so 825.47 kg of carbon footprint basically means it is equivalent to 1,37,578 hours of watching YouTube. Well, now just by comparing this, you can just try to think of that what is the total amount of carbon footprint that is being generated from these transactions. The second stat is about the electrical energy consumption. So per transaction, it takes up to 1737.82 kilowatt hour, which is equivalent to the power consumption of an average US household over 59.56 days. Well, so all these statistics I have collected from this Digiconomist Bitcoin Energy Consumption Index. So that actually does this energy consumption analysis for Bitcoin blockchain, and they provide that information. So by these two information, you can find out that the amount of electrical energy that is required for every transactions in the Bitcoin blockchain and the amount of carbon footprint that is being generated by every transaction of an Bitcoin blockchain. So that is actually massive. Now with this, if we just try to think of that how we can do an optimization in this front, or how we can generate an optimization in this front. Well, so people have tried to think of different kind of consensus mechanism on top of proof of work blockchain, and the early of them was this proof of stake or POS. So this proof of stake was possibly proposed in 2011 by a member in Bitcoin forum. There was no formal paper like the Bitcoin paper. It was something that was just proposed in the Bitcoin forum as a solution to this problem which are being there for proof of work blockchain. So the idea says that you make a transition from proof of work to proof of stake when Bitcoins are widely distributed. Well, so it is for the Bitcoin network, and the idea is that well, initially you start with proof of work, and when you see that well, the Bitcoins which are getting generated as a reward from the block mining, those Bitcoins are widely distributed across your network, across your Bitcoin network. Now, if I just try to compare between the basic idea behind proof of work versus proof of stake, so in case of proof of work, we see that the probability of mining a block, it depends on the work done by the miner. So if a miner has more computing power, the miner will have a higher probability to propose a new block. In contrast, in the case of proof of stake, it is the amount of Bitcoin that the miner holds. Well, so if you are holding 1% of the Bitcoin, you can mine 1% of the POS blocks. So the idea is something like this, that once this newly generated Bitcoins are evenly distributed in the community, then you give chance to individuals in the proportion to that Bitcoins that they possess. Well, so that the idea here is that well, it is a kind of more socialist kind of idea that well, this money has been equally distributed across the society. It is almost equally distributed in the society. Now, when the money is equally distributed in the society, the amount of money you are holding, you can be the leader for that percentage of time. Okay. So, if you are holding 1% of the total money, you can contribute to 1% of the decision making process. Well, something similar to that shareholding things, right. If you are holding 1% of the share, then you can take the decision for 1% of the cases. Well, so this is the kind of core idea behind proof of stake. So this proof of stake, it provides increased protection compared to proof of work. First of all, this executing an attack is expensive, because to execute an attack you need more amount of Bitcoin. Well, so because you can only propose new blocks which is proportional to the amount of Bitcoin that you hold. Now, to raise an attack you need more amount of Bitcoins, and also you have reduced incentive for attack. Well, so that way. So the attacker need to own a majority of the Bitcoin to raise an attack. Well, so that way the attack will have more effect on the attacker. So rather than gaining, the attacker will possibly lose. So that way it provides more protection compared to proof of work. Now, there can be different way this stake is defined. One way I have said that the amount of Bitcoin that you have, you can mine that proportion of newly block. So you can have a kind of randomization in the combination of stake, which is used in Next or Blackcoin. Another idea is to use something called the coinage. So what is the coinage? Coinage is the number of coins multiplied by the number of days you have hold a coin. So that means that also poses additional problem in case of attacker. These have been used in Peercoin. So that means if an attacker just gets some coin and say that, hey, I have this many number of Bitcoin, so I can generate a new block, it is not possible. You have to hold the Bitcoin for a longer duration. So it is something like that. If you have 100 Bitcoins and you have just have it for 1 day, it is equivalent to you have 1 Bitcoin holding for 100 days. Well, so that way this coinage make the idea more decentralized compared to simply finding out the ratio of the coins that you are holding. But this problem with proof of stake is that you need to hold the coin. So that is the kind of major thing, and you need to show that you have that much of coin. Another idea that got emerged around that time, it is called the proof of burn or POB. The proof of burn says that the miner should show proof that they have burned some coins. What is meant by burning a coin? Burning a coin means you send them to a verifiably unspendable address. Unspendable address means you send it to some address that can be verified, but no one is holding that address. So if you are sending money to that address, no one would be able to spend that money. Well, so this proof of burn, if you just think carefully, that you are also wasting some amount of digital money. So that way it is expensive just like proof of work, but you are not using any external resources. So what you are basically doing, that you are burning the digital currency, not the physical computing power. So that way people claim that, well, it is possibly more energy efficient compared to proof of work. Well, so in case of proof of work, you are actually burning the real resource, that means the computing power of your machine. In case of proof of burn, you are burning the virtual or the digital resource. Well, and proof of burn, that works by burning the proof of work mined cryptocurrencies. So the cryptocurrencies that you have, the Bitcoin that you have obtained through proof of work, you burn them. But the problem with this proof of stake and the proof of burn is that ultimately they depends on proof of work mined cryptocurrencies. Well, in case of proof of stake, you can start proof of stake only after the proof of work mined Bitcoins have been evenly distributed in the society, and in case of proof of burn, you need to burn certain proof of work mined cryptocurrencies. So you need to start with proof of work. So proof of stake or proof of burn cannot individually work like a bootstrapping consensus mechanism. You cannot simply start a network, a blockchain network, open blockchain network with proof of stake or proof of burn. You need to first start with proof of work, and eventually you can move to proof of stake or proof of burn. Well, so in that context, some other consensus mechanism had been proposed. One of them is this proof of elapsed time or POET. So this proof of elapsed time was proposed by Intel as a part of this Hyperledger Sawtooth, which is a blockchain platform for building distributed ledger applications. So you can look into Hyperledger Sawtooth, and Hyperledger Sawtooth uses this proof of elapsed time. So the basic idea behind proof of elapsed time is that each participant in the blockchain network waits for a random amount of time. So if you just try to remember the idea behind proof of work, So, the challenge which was there, that means finding out the nonce. So, the idea is that everyone would try for random amount of time, and the person who has been able to find out a solution, that person becomes the leader. And what I have to do, that eventually among the people who are there, I need to find out someone as the leader who is proposing the new block. So, the question comes that how I am going to choose the leader in an open network, and from that context this challenge response architecture came. Now, if I just think about the challenge in a different way, so what is that different way? Rather than providing them certain challenge, I just say that everyone need to find out a random number in between 0 and 100, and you need to wait for that amount of time. Well, and who will be wait less, for that person I will be considering as the next leader. Well, so that means the first person who would be able to finish that timer, that person becomes the leader. Well, that seems like a pretty simple algorithm, right? And that serves my main purpose. The only problem here is that whenever I am asking every people that you choose a random number and you wait for that amount of time, what is the guarantee that the person has chosen a random number between 0 and 100 and waited for that amount of time? So, I need to find out certain guarantee of this. So, for that purpose, what Intel does, they use a hardware logic here to verify that the proposer has really waited for that much amount of time. So, it utilizes special CPU instruction set which is called Intel Software Guard Extension or Intel SGX. Well, so this Intel SGX is a trusted execution platform. So, what is a trusted execution platform? A trusted execution platform is basically a hardware component where you can put certain logic, well, as a part of your operating system. So, this trusted execution environment divides your entire computing space into two parts. One is that called the untrusted world, and another is called the trusted world. Now, your general applications that you are typically using, those applications typically run on the untrusted world. Now, whenever you need to do some kind of trusted computing, that you need some kind of attestation or some kind of verification, that verification should come from a trusted world that no one should be able to change or no one should be able to modify. You can take help of this execution environment, which is basically a hardware component which is called a trusted execution environment, and that trusted execution environment can provide an attestation that, well, this particular content is verified. That means, say for example, if you just write with the hardware clock that the hardware clock has been ticked for 100 times, you are attesting this. So, that can be done from this trusted execution environment. So, that is a hardware component, and it is as such not possible to tweak this hardware component. Now, there are multiple different trusted execution environment which are available. One of the trusted execution environment is for the ARM processor, which is called ARM Trust Zone. Similarly, Intel has its own trusted execution environment which is called as the Intel SGX, Intel Software Guard Extension. So, you can use that kind of hardware component to provide such kind of trusted computing. Well, so this trusted code, it is private to the rest of the application. So, this rest of the application, they do not see this trusted code, and that way they do not be able to modify those trusted code. And this specialized hardware, it provides an attestation that the trusted code has been set up correctly. Well, so basically what you are doing here, you are taking up an hardware signature, and that hardware signature is providing a guarantee that whatever execution that has happened, that execution has really happened. So, for example, if you say that, well, I am setting up the timer to 90 clock ticks, then this hardware provides an attestation that, well, 90 clock ticks has actually been spent. Well, so that is being done by this trusted execution environment, and nowadays many applications are actually exploring this trusted execution environment for designing the applications. So here is an architecture of the Intel SGX, the simple a simple diagram similar to the one that I have just shown you. So here you can see that you have an untrusted code. In untrusted code, this untrusted code can create an enclave and call the trusted function. Now, when the untrusted code is creating the enclave and calling the trusted function, this call is going to this call gateway, from where after doing that hardware verification it comes to this trusted execution environment. So, under that trusted execution environment, the trusted function gets executed. So, after this trusted function get executed, it returns, and this return value is sent to the untrusted code, and the untrusted code continue with its processing. Well, so that means for the proof of elapsed time, what can happen that your untrusted code can say that will generate a random number and wait for that much of amount of time. So, generating this random number and waiting for that much amount of time, that can get executed within this this trusted code part as a trusted execution environment. Well, so that way you are actually getting an hardware attestation that well this particular code has been executed correctly and it has produced it has waited for the required amount of hardware clocked in. Well, so you are basically providing a hardware attestation. So, this is the way this Intel SGX actually works, and I have just tried to cover 3 different non proof of work consensus mechanism, this proof of stake, proof of burn, and then proof of elapsed time. Out of these 3, we have seen that proof of stake and proof of burn cannot be used for bootstrapping, whereas this proof of elapsed time can be used for bootstrapping, but proof of elapsed time that can work only on this Intel SGX platform. So, that is in conclusion that what we have seen, that proof of work is significantly costly. So, you can reduce that cost by moving towards proof of stake or proof of burn, but proof of stake or proof of burn that cannot be used for bootstrapping. So, that way we can have low cost consensus mechanism that can used from the bootstrap, that is the proof of elapsed time, but proof of elapsed time also has the limitation that it needs specialized hardware. So, that way the thing that I always mention, that you do not have any kind of free lunch. So, whatever you want to do, you have certain kind of trade off. Now, for your particular application requirement, you need to analyze such kind of trade offs and accordingly need to choose that what consensus algorithm you are going to use. Well, and consequently, what we see that all these consensus algorithms, they are primarily designed for an open network or a permissionless network. So, immediately the question comes that what about the enterprise application? So, as I mentioned that one of the major limitations for the enterprise applications is that you cannot have a significantly large network. So, you cannot use something like proof of work. Well, obviously, you can use proof of elapsed time there as well, because it does not need that kind of requirement. But again, if it happens to be that well 50% of the participants, more than 50% of the participants are compromised participant, even in that case proof of elapsed time fails. Indeed, later on we will see that you cannot make that 50% requirement to 0%. You can go something up to 33%, if I tell correctly, that we will see later on. But you always have certain requirements from the society that well this much of participants in the society need to be good, at least this much of participants in the society need to be good to reach to a consensus. With that we complete our discussion on the consensus mechanism in a permissionless model or a open blockchain network. So, from the next lecture we will start our discussion on the consensus mechanism on the closed blockchain network or the permission blockchain network. So, thank you all for attending this part of the lecture. Hope to see you all in the next lecture.